We are now in chapter 14, and on the first page of our chapter 14 packet, we're going to talk today about verifying trig identities. A trig identity is something that is true. So if one side is exactly identical in value to the other side, we call it an identity. For example, a common identity that you might be aware of are just mathematical equations that we know are true. For example, if you look at x plus 1 quantity squared, if you were to multiply, double distribute, FOIL that out, we would get that trinomial. That we know is true. What is on the left is equal to what is on the right. Other identities start to appear as we move through this unit, and we're going to work on verifying an identity. Verifying an identity means that you are showing that the equality does exist. So some things that we do know from the previous chapter, in chapter 13, are reciprocal identities. So those are the ones that relate sine, cosine, and tangent to their reciprocals. So the sine function, the cosine function, and the tangent function are all related to its reciprocal, as 1 over cosecant of theta is sine, 1 over secant of theta is cosine, 1 over cotangent of theta equals tangent. And the reverse is also true. Now some tangent identity, these are quotient identities, we know are true because of the relationship that we had studied in the last chapter. So tangent, we had talked about being opposite over adjacent, which ended up being your y value over your x value when we're taking a look at a angle in standard position. So y over x. Y is also sine, so if you replace y with sine, you get that the numerator is sine of theta, and then the denominator being x is cosine of theta. Cotangent being the reciprocal of tangent would mean that cosine's on top and sine's on the bottom. The next set of identities we're going to write out and prove. There's 3 Pythagorean identities. The first one being, and we will prove this in a minute, sine squared of theta plus cosine squared of theta is equal to 1. The second one being 1 plus cotangent squared of theta equals cosecant squared of theta. And then the last one being tangent squared of theta plus 1 equals secant squared of theta. So how is the first one true? If we think about our unit circle and we think about the fact that the equation of a circle with a radius of 1 yields the equation x squared plus y squared equals 1 squared, or just 1, then we know for sure that that any point that falls on that unit circle should satisfy that equation. X is, we associate x with cosine, where cosine of theta is equal to x over the radius. In this case, the radius is 1. So if we replace the x with cosine and the y with sine, then we get our first Pythagorean identity. Cosine squared of theta plus sine squared of theta is equal to 1. So with trig functions, we typically write the squared not on the outside. So here's what I'm going to show you guys. We don't write cosine squared theta like that, because then the confusion is that we're taking cosine of theta squared as opposed to squaring the cosine function. So when we say cosine squared theta, this is the equivalent of cosine of theta times cosine of theta, which is what we're trying to say here. X times x, cosine times cosine. So remember to move that squared next to the cosine, so we know that it's cosine being squared and not theta. Okay, so the second trig identity we can get from our first one. So let's say we had cosine squared of theta plus sine squared of theta. This is where we left off in the first one. And it's true if I divide, we have a total of 3 terms, 2 terms on the left and 1 on the right. if I divide every single one of those terms by the same thing, that's mathematically correct. So in this case, I'm going to divide everything through by sine squared of theta. So if I divide the quantity on the left by sine squared of theta, I would have to do the same on the right. Cosine over sine is the same thing as cotangent. So cotangent squared of theta plus sine squared divided by sine squared is 1. And then what's the reciprocal function of sine? 1 over sine squared is the same thing as cosecant squared of theta. So there is my second identity proven. And then what do you guys think we do to prove the last one? So hopefully you thought of it and you came up with the idea of starting with what our original Pythagorean identity and dividing by cosine now instead of by sine. So dividing every single one of the three terms by cosine squared of theta. And getting sine over cosine squared is the same thing as tangent squared of theta. Cosine squared plus or over cosine squared is 1. And then 1 over cosine squared is secant squared. S goes with the C. So this is my third and final Pythagorean identity. Just be aware that knowing these identities are essential, I would say, for pre-calc honors next year, just for this course in general. Of all of the identities we're going to study, I would say that these are the ones that are on these page is the ones on this page is essential to understanding further concepts that we'll study in the next few sections. So make sure you guys take a look at this and understand how we derived it, where it came from, and then also how to replace things. So those are the original ones. So when I say replace things, it means being flexible and fluid with those equations that you see there. So for example, if you take the first equation and you have sine squared of theta and plus cosine squared of theta, notice that I switched the two, sine squared and cosine, and it still means the same thing. So sine squared plus cosine squared of theta equals 1. If I subtract sine squared to the other side, then it's also true that cosine squared of theta is equal to 1 minus sine squared of theta. So that's something that might pop up in a problem that you're to recognize. You can replace 1 minus sine squared of theta with cosine squared of theta, or vice versa. If you solve for sine squared of theta, it's equivalent to 1 minus cosine squared of theta. So being able to, again, recognize sine squared is 1 minus cosine squared is going to become important later on.